Hello, cowboys and cowgirls. This is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School, and I want to welcome you to this, my last lesson. It is on transformations to achieve linearity. So here are the principles of logarithms and exponents that you will need for this lesson. I'm going to urge you to pause the video right here so you can review this and refresh your recollection. Okay. An equation is linear if it is in the form y equals a plus bx. What if the data shows a curved relationship? Well, sometimes the data can be transformed to achieve linearity. Once the data has been transformed to achieve linearity, we can use our least squares regression procedures to generate a useful model for making predictions. So there's two transformations that we're going to talk about in this unit. One is the power model and one is the exponential model. On this slide, I want to talk about the powers model. So how do you know when you're going to use the powers model? To use the powers model, what I want you to do is you would take the log of the x variables and the log of the y variables. Then create a scatter plot of the log of x versus the log of y to verify whether there is a linear pattern. If the scatter plot confirms a linear pattern, then you should run a regression on the transformed variables, and you will write out your equation. It will be the log of y equals the intercept plus the slope coefficient times the log of x. With that, using the principles of exponents, you're going to make a prediction. Okay. And here is the other type of transformation. This is the exponential model. So with this model, what you would do is you would take the log of the y variable only. You do not take the log of x, but you will take a scatter plot of x versus the log of y and look to see whether that scatter plot has a linear pattern. If the scatter plot has a linear pattern, then you run a linear regression on the variable log of y using x as the independent variable. After that, you write out your equation in the form log of y is equal to the intercept plus b1, the slope coefficient, times x. And from that, using the principles that I showed you before, you will make predictions. Now this can be done in both the log of base 10 or in the natural log, or for that matter, using any base. So here I've summarized pretty much everything you need to know for this unit. In the green font, I have the power model. It's good for inverse models and the quadratic models and models that are like that. In this model, you take the log of both the x and y variables, and that's what you plot in your scatter plot. Then I have the transformed equation that you would write out from your computer output. And then using the principles of logarithms and exponents, you'll get to this prediction equation right there. And I also have in red font the exponential model. This time you take the log of only the y variable and you plot x versus the log of y. And as you can see, you can do it with either natural log or log base 10. After that, you write out your transformed equation based on your computer output. And using the principles we talked about earlier, you can make a prediction. So I'll do one of each. The table below shows the computer output from the regression of the log of the weight of pizzas in ounces on the log of the diameter of the pizzas in ounces. So first thing I see is that both variables have been transformed using the log function, and we are transforming using a log base 10. So when I write out the equation for the regression line, I write it out like this. The predicted log of the weight is equal to minus 0.06 plus 2.0 times the log of the diameter. And I actually use the names of the variables in there because that adds context rather than putting in the log of y and the log of x. So now I have my transformed equation based on my output, my computer output, and the next thing I need to do is predict the weight of a pizza when the diameter is 20 inches. So basically what I'm going to do is I'm going to put 20 in for the word diameter and figure out what my predicted weight is. So here's my formula. The predicted weight is 10 to the power of minus 0.6 plus 2 times the log of 20. With my calculator, I find that that is equal to 100.5 ounces. So let's do one using the exponential transformation. Table below shows the computer output for the regression of the log of housing prices on the year after 2000. So here I see that I've only taken the log of the y variable, and I'm doing so with the natural log. And year is the year is not in log format. So I write out the equation like this. My predicted log of the housing price, and I make sure I use the natural log symbols and e as my base, just to be clear, is equal to 6 plus 0.40 times the year. That's my transformed equation. And now I have to use it to make a prediction. So I want to predict the price of a house in year 18 or 2018. So my predicted price is equal to E raised to the power of 6 plus 0.4 times 18. And that, my calculator tells me, is 828,000. So here's an example of each. So one final thing that I want to make clear: how do we choose the best regression model? Well, the first step, if you're starting from scratch, the first thing you want to do is you want to take the scatter plot of the log of x and the log of y, and also create a scatter plot of x versus the log of y. And you're going to look at both of them and compare. What you're basically looking for is which of these models has a linear pattern. And you're going to go with the one that has the linear pattern. But if it's hard to tell which one has a linear pattern, then the next step is to do this. You want to fit a least squares regression line to both sets of transformed data, and then look at their residual plots to see which one has the most random scatter. Okay, that's the second step. And if that isn't conclusive in deciding which is the best regression model, then the last thing to look at is whether you have to look at the residual. If the residual plots look roughly the same, then the last thing you look at is the values of s and r squared to decide whether a power model or an exponential model is the better choice. Usually you only have to look at the scatter plots to make a conclusion, but here is the procedure if the scatter plots are ambiguous. Just as a reminder here, the AP exam sometimes asks questions. We call them question 6 questions. They're investigative tasks, and they might show you something. They might walk you through a procedure that is slightly different than the ones we've talked about. On the top here, I have a multi-regression analysis, which has more than one independent variable, and so I've written it out there. Of course, you have to make a change to the number of degrees of freedom. One year, they had the students in a question 6 investigative question analyze a dummy variable, and in this case, an independent variable takes on only one of two values, 0 or 1. So I have that example where x is equal to 0 if the subject is male, and x is equal to 1 if the subject is female. So that was one type of question. Another type of linear regression is the linear trend model, but there's also seasonal trend models and cyclical models. So there's all kinds of regression models that we can discuss. What do AP students really need to know? This here is a pretty good list of everything that you need to know for this unit here. You need to be able to interpret the slope coefficient and the y-intercept. You need to be able to interpret the standard error of the slope coefficient and the standard deviation of the residuals. interpret the correlation coefficient and the coefficient of determination. You have to find and interpret the residual plot. Write the least squares regression equation from the computer output. Write the least squares regression from a set of summary statistics, and that's using the formulas on your AP formula sheet. You need to be able to do an ICCI for a t-test for the slope coefficient, an ICCI for a t-interval for a slope coefficient. You need to know about outliers, high leverage points, and influential points. You need to know what is extrapolation. And finally, you need to know about power and exponential transformations. That's a lot in these 2 chapters. So just a quick review. Population true regression has a line like this. The sample estimate regression has a line like shown in the second line. In the sample estimate, we have only data from one sample, whereas in the population regression, we use all of the data from the entire population. Terms to know: you should know S, the standard error. You need to know R, the coefficient of determination, and how to interpret it. You need to know B, the slope coefficient of the regression line, and how to interpret it. You need to know the standard error of the slope coefficient and how to interpret it. And here is a brief summary of the 2 regression procedures: the t-interval for the slope of beta, that's my formula right there, and how I get my t, my critical t. And here is, in the second procedure, is the linear regression t-test for slope of beta. There's my null and alternative hypothesis. You would need to know how to calculate a t-statistic using the appropriate t-statistic. You need to report the number of degrees of freedom and the p-value. And here I have the requirements of the ICCI for questions in this unit. I want you to name the procedure and check the conditions. We have the linear condition, independent condition, normal condition, equal variance or equal standard deviation, and random selection. So that basically is everything you need to know for chapters 3 and 12. Thank you for listening.